everyone. In this video, I will try to touch the topic of curvilinear coordinates, which are basically generalized coordinates. At the end of this video, I hope you get an idea of it, but let me start with why I'm interested in this topic. Basically, I have a pet peeve. Let's demonstrate my pet peeve with the help of Dave and Amy. Dave asked Annie to give him instructions so that he could reach her and they'll go to school together. Annie says to him, Dave, move forward, turn around, and then move forward, you'll find me. What Dave does is he moves forward, turns around, moves forward again, but he reaches a pharmacy. This is not where he wanted to go. This is what happens a lot when a person is giving instructions to another. A lot of confusions happen because instructions are not clear. What to do about this? Well, scientists and mathematicians know that this is a problem, and they also have to refer to different points and use uh, those points to, positions to in their calculations or whatever they're dealing with. So what they do is use standards. Let's say we have two rays, one is horizontal and we name it x-axis, and the other is vertical and we name it as y-axis. So the point at which these two meet is what we call the origin point, and we can draw a scale on the axis. So we can set a unit for describing. Let's say we have a point we have to describe, and I describe it by saying that by moving 4 units along the x-axis and moving 2 units along the y-axis, I can reach that point. This is how I standardized instructions. The system I'm using here to give these standardized instructions is Cartesian coordinate system, or also known as rectangular coordinate systems, in 2 dimensions. I'm referring to the 2 dimensions in this diagram. But we can also go in 3 dimensions. We can use x-axis, y-axis, and another axis that is perpendicular to these. I name it the z-axis. And we'll have a 3-dimensional coordinate system. And just as the point P is shown here, we can give its position by mentioning how many units we moved along the x-axis, and similarly for y and z-axis. This is the extension of the description I gave you for 2 dimensions in 3 dimensions. But there are other ways too. Like what? We can mention the position of a point instead of mentioning how many units to move along the x-axis and y-axis by mentioning that this many units as a straight line, and move the straight line to, let's say, 120 degrees. We can make a scale for it to exactly measure the units and to measure the angles. So this system is what we call the polar coordinate system. Sorry. This is what we call the polar coordinate system. And we can use both methods to describe the same point. Like shown here, it is a point. I can describe it in terms of x and y, but also as in terms of r and theta or phi, or I can call the angle whatever I want. I can use an angle, like let's say this point is, let's say, 35 degrees. So I can use both methods to describe the same point. And we can also move from one coordinate system to another, meaning that if I have the values in x and y, I can calculate the values in r and theta. Let's say that Dave had measured the position of a point in x and y coordinates and any head measured in r and theta, they can exchange the information that would not be wrong, which would produce the same results by using some transformation equations. Here the points are shown in turn transformation in how you can transform these points. So what happens when we go in 3 dimensions? We saw what happens when we go in 3 dimensions for Cartesian coordinates. But for a circle, when we go in 3 dimensions, we could form a sphere. And for any point, let's say here's a point, I have a point here. I can mention it as a point on the surface of a sphere. But this is not the only way. I can also mention it as a point on the surface of a cylinder. If I take a circle and extend it along a straight line, it will form a cylinder. And I can take a point on its surface, and I can give an origin and define values for a cylinder like its radius and its height and whatever is associated with a cylinder, and I can use those values to describe the position of a point. And again, there are other ways too. We can take an ellipse, put it on a Cartesian coordinate system, and we can give its coordinates, or we can form another coordinate system according to the measurements of an ellipse, and in 3 dimension it would become ellipsoid or spheroid, whatever you want to call it. And again, we can have a parabola, and we taking it into 3 dimensions, we can form paraboloidal shapes, and we can use them to describe points. So we can use any curves in this world, and hence we have the term curvilinear coordinates, mentioning we can use any sorts of curves. We can form coordinates using those curves, and they are generalized. Oops, sorry, I missed the equations, but we can give them equations. And why is this useful? This is useful because this is more general. I can take any shape, any curves, and any coordinate system, and give use that system to describe a position. And also, some coordinate systems make the calculations easier than other coordinate systems. Like some of the calculations are easier in spherical coordinate system or cylindrical coordinate system than they are in Cartesian coordinate systems. So this is useful because this is a more general idea. And if you've had if you study physics and you have heard that the laws of physics are the same in all inertial reference frames. This is connected to that. This helps us keep the law, not keep the law same, but this helps us with the idea that any calculations we make in any system produce the same results. We can calculate in any system and we can transform to any other system, but the results will be the same, making the laws of physics same in all reference frames. Thank you.